It's time to get your arrows popping. Ladies and gentlemen, this is Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about graphing logarithms. That's right, you, me, and a whole lot of logarithms to graph today. That's right, get ready. But first, won't you go ahead and be so kind as to subscribe to the YouTube channel Fort Bend Tutoring. I would really appreciate that. And don't forget to click on the bell icon so that you can be notified when we are uploading new and fresh videos for you. That's right. Well, let's go ahead and move on and check out the topics of this video. We're going to be providing you with parent functions, transformation maps, 6 examples, people, multiple techniques, different bases of the logarithms, and step-by-step instruction in how to graph each and every one of these logarithmic functions. Oh yes, I am excited about this video. Here we have the 6 logarithmic functions that we'll be graphing in today's video, guys. Check them all out. Notice the different transformations that I have in store for you. So we have a lot to discuss, and let's just touch on a few of the basics here. Notice that we have our parent function f of x equals to log base b of x, where x must be greater than 0, b must be greater than 0, and b cannot equal to 1. And just for added value, we have the following tips here at the bottom. All graphs of logarithmic functions of this type that you see here on the screen will pass through the point 1, 0. The y-axis is the vertical asymptote of these graphs. If b is greater than 1, then your function f of x will increase as x approaches infinity. And if you'll find that b is less than 1, but yet still greater than 0, then f of x will be decreasing as x approaches infinity. So just some fun facts for you to keep in mind. From here we have example 1. All right, so you have your parent function f of x equals to log base 2 of x. The first thing you may want to identify is the vertical asymptote. In other words, where the graph cannot touch because it'll make the graph undefined. Well, you'll find that value by setting the argument. That's right, this value right here equal to 0 in order to find out what your vertical asymptote is. So here we'll set the argument x equal to 0, and you have it. That is the vertical asymptote, the vertical line, x equals 0. Now, the approach that I take in order to find the points that I want to use to graph this function is going to be consistently as follows. I'm going to start out by identifying that first value where the function is undefined. In other words, it's going to be very similar to that value we found for the vertical asymptote. And that is 0 will make this graph undefined. If we were to plug in 0 into log base 2 of x, plugging that in, log base 2 of 0 is undefined, guys. The next thing I'm going to want to set the argument equal to is the reciprocal of our base. Well, the base of this logarithm is 2, right? And so the reciprocal of 2 is 1/2. Plugging in 1/2 into the function to get the y value, you'll have the following. We'll have f of 1/2 equals to log base 2 of 1/2. Well, in doing so, I can show that this is log base 2 of 2 to the negative first power, whereas we can simplify then to end up with a result of -1. So notice that plugging in the reciprocal of our base as the argument here, we're able to end up with a result of -1. So I have -1 when x equals to 1/2. The following value that I will want to try is going to be the value of 1. I want to see what happens when x equals to 1. The way I'll be able to evaluate this is to have f of 1 equals to log base 2 of 1. Well, we'll be able to manipulate the problem and simplify by rewriting 1 as 2 to the 0 power. Then using our logarithmic properties, this will simplify to give us a result of 0. So when x is 1, y is 0. The next value that I'm looking for is our base to the first power. Well, our base being 2, 2 to the first power gives you 2. And once again, simplifying this, you'll have f of 2 equals to log base 2 of 2. And because your exponent on that base of 2 is 1, the result will be 1. So we have 2, 1. Similarly, we're going to be plugging in 2 to the second power. Your base to the second power is the next value I'll use. And in this case, 2 squared is 4. So when plugging in 4 into our function, you'll have log base 2 of 4, which can be shown to be log base 2 of 2 squared, which simplifies to give you a result of 2. So I'm utilizing these values to construct an XY chart that I can rely on to graph the logarithmic function. And I'll use those values each time. So we first start out by setting the argument equal to 0 so that we can find out our vertical asymptote as well as the first value that makes this function undefined. And then the next thing is we'll want to find out the value of x that makes the argument equal to the reciprocal of the base. That's how we ended up with this 1/2, because obviously our base of this logarithm is 2. And if you were to flip that, you'll end up with 1/2, right? From there, we wanted to find out what happened when the argument equaled to 1. And we evaluated that to find out that result would be 0. Then we took our base to the first power, that base of 2 to the first power equals to 2. And we used that for the argument there and simplified to get a result of 1. And then finally, we had our base of 2 raised to the second power. 2 to the second power gave us a value of 4. We plugged that into the function to get a result of 2. So that gave us our values that we can now use to graph our logarithmic function, guys. Notice at the bottom of the screen, I've already identified that our vertical asymptote is the equation x equals 0. Let's start by graphing that on our Cartesian plane here. So we've identified in yellow the x and y axis of the graph so you can clearly see it. And now what I'm doing is I'm using a dashed line to identify what the vertical asymptote is. Now I'm going to utilize the points that we generated to plot the graph. We have our first point, which is going to be 1/2, -1. So we go a half to the right and then down 1, and it'll give us a point right here. Then we'll have a point at 1, 0. Have a point here. Then the next point is going to be at 2, 1. That gives a point right here. And then we have a point at 4, 2. So 1, 2, 3, 4 to the right, and then up 2 gives us a point right here. And now we'll go ahead and we'll define the graph by going through our points. Because we have a vertical asymptote here, we can get close to 0, but not touch 0. And you'll end up with the following graph of our function f of x equals log base 2 of x, guys. Now to continue with identifying what our domain is, you can use the graph to determine what that's going to be. For instance, our domain is going to be from 0 to positive infinity, not including 0. And then the range is going to be -infinity to positive infinity. And that's going to be the result of problem number 1. All right, that's it, guys. And of course, if you wish, you can red box your answers, guys, just like that. So we have our domain, we have our range, as well as the vertical asymptote. And of course, we have points from the graph that you can include in your result as well to prove that your graph is correct. Amen, amen. All right, let's move on. And also, I would like for you guys to please donate. There's going to be a donation link in the description box and on our About page. Your donations helps us create more FBT videos for your viewing pleasure and for your educational endeavors. All right. So by all means, donate what you're able to, and we will put that to good use in producing more FBT videos. Moving on, guys, we have problem number 2 now. With problem number 2, you have f of x equals to log base 2 of the argument x minus 3. So in order to find out what the vertical asymptote is, you want to set that value of the argument equal to 0 and solve for x. So we have x minus 3 equals 0. Adding 3 to both sides of the equation and simplifying, you'll now have x equals 3, which is your vertical asymptote. Also remember that it's that same value that we just identified, that value of 3, that will make the function undefined. All right. So we're going to start by showing that that value of 3 gives us an undefined result. From there, I like to use the reciprocal. All right. So let's see what happens. What value of x can we use to make that argument equal to the reciprocal of the base, which is 1/2? Well, by adding 3 to both sides, we'll find that x needs to be 3.5 in order to have the value of the argument equal to the reciprocal of the base, which is 2, right? So having a base of 2, if you were to flip that, the reciprocal, you would end up with 1/2 as a result. Well, by plugging in 3.5, you'll generate that reciprocal that you're looking for. And then in simplifying, as we did in the previous problem, that 3.5 minus 3 gives you 1/2, which can be written as 2 to the negative first power, which gives you a y result of -1. Just saying that out loud makes me want to make sure that I show you guys. So here we go. We have f of 3.5, right? So plugging that in, you'll have log base 2 of 3.5 minus 3. Well, this gives you log base 2 of 1/2, right? All right. From there, you can say that you have log base 2 of 2 to the negative first power, which simplifies to that -1 right here. So that's what I'm talking about as far as utilizing these values to generate points on our graph. The next value that I want that argument to become is going to be 1. So if we have x minus 3 and I want it to equal to 1, we'll add 3 to both sides to figure out that I want x to equal to 4. So by having a value of 4, that means that the argument is equal to 1 now, and then rewriting that 1 as 2 to the 0 power, you'll end up with a result of 0 for y. Next, you'll want the argument that x minus 3 to equal to 2. Let's see what that looks like. You'll have x minus 3 equals 2. By adding 3 to both sides, you'll end up with x equals to 5. If we were to plug in 5, guys, you'll have log base 2 of 5 minus 3. This gives you log base 2 of 2, which will have a result of 1. All right? So when x is 5, the result is 1. 2 to the second power value. In other words, you'll do the same and look for when the argument equals to 4, and you'll find that the argument x minus 3 equals to 4 is the setup, and then you'll find out the value of x will need to be 7. Well, plugging in 7 and ending up with that 2 to the second power, in other words, that value of 4 as a result, we'll end up with a y value of 2. So in other words, when x is 7, y will be 2. Let's make sure I show you so you can get it. We'll have f of 7 equals to log base 2 of 7 minus 3. This gives you log base 2 of 4, which is the same as log base 2 of 2 squared. And now, simplifying using your logarithmic properties, that log base 2 of 2 simplifies to give you the result of the exponent, which is 2, and that's how we generated that y value. So once again, guys, this is the process that I use to generate the coordinates, the points that I use to graph logarithmic functions. After you get some repetition into this process will become that much easier for you to duplicate and replicate when you're doing your assessments and also on your journey for mastery of this concept. Graphing this, we're going to begin with the vertical asymptote. I want to show that boundary where the graph can never touch. So at x equals to 3, we'll have a dashed line representing the vertical asymptote. All right. And also don't forget, guys, that we have a video on vertical asymptotes as well that you can get some more examples when dealing with rational functions, okay? So we have our vertical asymptote. Then we're going to be plotting our points. The first point we have is 3.5, -1. So at 3.5, -1, I have my first point. Then at 4, 0, I'm going to be here. Then we're at a point at 5, 1. Like so, and then we'll be at 7, 2. Is 7 on this graph? 1, 2, 3, 4, 5, 6, 7. Yes, it is. Great. And we'll be at 7, 2. Let's go ahead and connect the dots here. So once again, we're going to be close to the asymptote, not touching it though. And there we go with the arrow on the end. There we go, guys. So this is your graph of the logarithmic function log base 2 of x minus 3. Done and done as far as the graph is concerned. However, your domain is going to be from 3 to positive infinity. And your range is going to be all real numbers. In other words, negative infinity to positive infinity. Once again, notice how I prefer to do especially the range after I graph it. Not necessarily the domain. I can do the domain at the beginning, but I just have a preference when dealing with these logarithmic functions to go ahead and just settle up with the domain and range after I have graphed it. All right, so let's go ahead and red box it. We have our vertical asymptote. We also have our domain and our range, people. There we have it. All right, on to the next part. Here we have the expanded form of our parent function f of x equals to log base 2 of x. So in this expanded form, what I'm trying to show you is the transformations that are possible when encountering problems such as these. If your a value is negative, for example, there will be a reflection, a vertical reflection across the x-axis. So you can scan through these to see the different changes that you'll encounter depending on the problem and the different transformations therein. Here, I'm going to continue on this next page here where, for instance, the C value will tell you about your horizontal shift. The D value will be your vertical shift. In other words, move the graph up and down. All right. We also have a video dialing into these transformations called transformations of functions. So make sure that you check that out. In this case, also, when it's expanded, when you have additional terms like this, you'll find that your vertical asymptote will be the same as the equation x equals to c. So let's continue. Here we have problem number 3, and as promised, we're going to tackle this problem a little differently because I'll be introducing transformation maps as an option to what I've shown you thus far. You can continue the same method and process that I showed you earlier in the video in order to graph your logarithmic functions, but I also wanted to give you an alternative to consider. So for instance, what you're seeing here on the left side there, the XY chart that I gave you, is going to be basically the f of x, the parent function of log base 2 of x. That's what you have here on the left side. We're going to use this parent function in order to find out what the points should be using a transformation map for our new function q of x. Notice that that function is log base 2 of x plus 2 plus 3. Utilizing the expanded form that I just showed you, you should be able to identify that you have two transformations here. One is a horizontal shift 2 units to the left, and you also have a vertical shift 3 units up. Okay, so this is what we're expecting from this graph just based on the transformations they've included. So what we'll do now is we'll create a transformation map to identify those two transformations. If you have a horizontal transformation, it affects the x value, and every vertical transformation affects the y value. And so for your transformation map, we'll say that for every point in the original graph, in your new function, you'll need to subtract 2 from every x value, and you'll need to add 3 to every y value. So it's this transformation map here that we can utilize on the parent function's point to make our new points here. Also, let's not forget that in order to find out the vertical asymptote, you'll need to set the argument of x plus 2 equal to 0 and then solve for it. So that means that my vertical asymptote is x equals to -2. Let's go ahead and red box that one real quick so you'll have that identified. X equals to -2 is the vertical asymptote. Now to use the transformation map to get our new points. So remember, we're supposed to subtract 2 from all the x values and add 3 to all of the y values. So that means that instead of 0, I'll have 0 minus 2 is -2. If a y value is undefined, it will stay undefined. Then you'll have 1/2 minus 2. Well, that'll be -1.5. Adding 3 to the y value, -1 plus 3 gives you a result of 2. Then if I say 1 minus 2, you'll end up with -1. And then adding 3 to the y value, 0 plus 3 is 3. Plugging in 2, 2 minus 2 gives you 0. Plugging in 1, 1 plus 3 is 4. Plugging in 4, 4 minus 2 is 2. And plugging in 2, 2 plus 3 gives you 5. So these will be the points that I use to graph q of x. All right, so let's go ahead and continue. Here, what you see before you is the graph of your parent function. I wanted to use this as a contrast to our new graph of q of x so that you can see the result of the transformed function compared to its parent function. So let's go ahead and start graphing here. We have our asymptote that's going to be at x equals to -2. So we'll have a dashed line going through -2 on the x-axis, arrows on both ends. And then plotting your points, you have a point at -1.5, 2. -1.5, 2 is here. You have a point at -1, 3. -1, 1, 2, 3 is here. You have a point at 0, 4. 0, 1, 2, 3, 4. Okay, and then you also have a point at 2, 5. 1, 2, and then 1, 2, 3, 4, 5. So you'll be extra close to your vertical asymptote, and you'll be going through the points that we've identified here. Arrows on both ends, and there is your transformed graph. So notice, guys, that we already expected the horizontal shift to be 2 places to the left from the original graph, as well as vertically shifted up 3 places above where we were. So that is pretty clear based on the original graph compared to the new graph of q of x. Now, looking at that domain of q of x, your domain is going to be from -2 to positive infinity. And your range is going to be, once again, all real numbers, negative infinity to positive infinity. And let's red box it, people, just like that. There we go. Got a box around the answers. That's right. We just showing off here. That's all we doing. We just showing off to the teacher. We know what we doing. Watch out, back up. Here we go. Give my A. Thanks very much. There you have it. All right. Let's move along. Here is a reminder to set up a paid online tutorial today with me, Mr. Whitt. That's right. You can hire me as your personal one-on-one math tutor, guys. That's right. If you want to get your learn on with Mr. Whitt, go right ahead and sign up. Holla at me, and we'll set up a paid online tutorial where you and I can get to work on mastering the content in your math class. So check it out at the website, fortbintutoring.com, guys. And moving on. Here we have problem number 4. So in problem number 4, we have more transformations to look at. Here the equation is y equals -2 times log of base 3 of x plus 1. So what do I expect by analyzing this equation? Well, for one, I see a reflection across the x-axis. All right, I see that vertical reflection. All right. Other things that I notice is I notice a vertical stretch of 2 because that absolute value of A is 2. And I also see that we'll have a vertical shift up 1. That D value is 1, so that means we're going to be moving the graph up 1, like so. And let's not forget also about that vertical stretch. So we had that vertical stretch there. That's going to have a scale factor of 2. All right. So there we go. So that means that there are going to be 3 transformations in this problem compared to the original graph, that original parent function of log base 3 of x, by the way. And what I've done for you on the left side is I've given you the points from that parent function of log base 3 of x. So even though we didn't look at that exact graph earlier in this video, I'm providing you with the values that you would have come up with if you would have used that exact process that I presented to you earlier. All right. Now, let's not forget the vertical asymptote, right? So for the vertical asymptote, you want to set your argument of x in this case equal to 0 and solve for it. Well, it's pretty much already solved for, right? We're just going to have the x equals 0. So that is your vertical asymptote for problem number 4. If we're going to draw out our transformation map, we'll say that for every original point on the graph of log base 3 of x, in order to come up with our new graph, we're going to keep x as it is. However, you have a vertical reflection, you have a vertical shift, and you have a vertical stretch. So that means we'll need to multiply the original y value by 2 and then add 1 to it. So the x value remains the same, whereas the y value you'll need to multiply by -2 based on the reflection in the vertical stretch, and then add 1 to it because of the vertical shift. Okay, so what you can do with this then is just bring over all of your x values. You'll have the 0, the 1/3, the 1, the 3, and the 9. All of that remains the same. And then by multiplying the y values by -2 and then adding 1, remember if it's undefined to begin with, it'll stay undefined. But when it comes to the -1, -2 times -1 is 2, and then 2 plus 1 gives you 3. Then you'll have -2 times 0 is 0, 0 plus 1 is 1. You'll have -2 times 1 is -2, -2 plus 1 gives you -1. And then -2 times 2 is -4, -4 plus 1 is -3. So these are the values that we can use to graph our logarithmic function here. So here, once again, in comparison, you have on the left your parent function. On the right, you have your new function after the transformations and using that transformation map. Notice that both of these functions have the vertical asymptote x equals 0, so we don't have to add anything there. However, when plotting our points that we have on the right, you'll have 1/3, 3. So at 1/3, you go up 3, 1, 2, 3. Like so. And then you'll have a point at 1, 1. 1, 1 is here. You also have a point at 3, -1. 1, 2, 3, and then -1 is here. And you have a point at 9, -3. That's going to be off of the graph, but let's see if we can get there. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then down 3. That'll be about right here, guys. So graphing this, you'll have the following. Remember there was a reflection across the x-axis, so it's going to be reversed from the previous one, okay? It's going to be flipped. And you end up with this graph right here in black, guys. This is the graph of the function y equals -2 times log base 3 of x plus 1. The domain of this is going to be from 0 to positive infinity. And your range is, once again, -infinity, the lowest value, to the highest value. You always start out with the smallest value to the largest value, guys. And now, red, box it. We have a vertical asymptote of x equals 0. We have our domain from 0 to positive infinity. We have our range of all real numbers. And this, in black, guys, is the graph of the function for this problem. Remember, the one in orange there, that was your parent function to show you in comparison the different transformations that were performed on that graph to get the one we have now in black. All right, let's continue. We have problem number 5. And so for problem number 5, we're going to go back to our first method of just generating those points and moving forward. So I wanted to show you guys a couple of the transformation map problems, and you may prefer that. That's great. I'm going to go back to what I was doing at first, okay? So starting out, we're going to start with our vertical asymptote by setting the argument of x minus 4 equal to 0 and solving for that. All right, so here we find out that the vertical asymptote is x equals to 4, and we'll go ahead and throw that in a red box. So that also tells us that at 4, the function is undefined. All right, you then want the argument to become the reciprocal of your base. Well, the reciprocal of your base here is going to be 2. So you can set the argument x minus 4 equal to 2 and then solve for that to find out that what you want x to be in this case is 6. So when you have x is 6 and it equals 2, your reciprocal of your base, then that y value is going to be -1. Then you'll want to see what happens when the value of the argument equals to 1. Well, how do you get there? You'll say that x minus 4 equals 1, and then you'll solve for it. And you'll find that you'll want your value of x to equal to 5. So if the argument's value is equal to 1, well, we'll just rewrite that as 1/2 to the 0 power to give you a result of 0. Okay, so once again, let me give you the slow motion on that so you can see how that works out. When you have f of 5, you'll have log base of 1/2 of 5 minus 4. This then gives you log of 1/2 of 1. Well, once you have it in this form, you can say that this is 1/2 to the 0 power because that equals to 1. Then you simplify this to give you 0 as a result. And there you have it. That's how you go about doing it. Then you'll want the argument to be set equal to the base to the first power. In this case, our base is 1/2. 1/2 to the first power is 1/2. So you'll have x minus 4 equals to 1/2. And then when you solve for that, by adding 4 to both sides, you'll find that you'll want your value of x to be 4.5. Okay? So when it's 4.5, you'll end up with your base to the first power. So once simplified, the end result will be 1. Then you'll want to solve for your base when it's squared. 1/2 squared is going to be 1/4. So once again, solve for x. And you'll have x equals to 4.25. So 4.25 will be the x value. And after simplifying using your logarithmic properties, your y value will be 2. And this, once again, is how I consistently generate the points that I will need to graph the logarithmic functions. Notice that in this method, I didn't have to be concerned about what transformations were occurring. Bottom line is my graph is going to be exactly as it should be, including the vertical asymptote. So showing what that looks like, I'm going to begin with my vertical asymptote of x equals 4. So to the right of the origin, 1, 2, 3, 4, I'm going to have a vertical line indicating that x equals 4 is off limits. Then I'm going to plot my points. I'll have 6, -1, 1, 2, 3, 4, 5, 6, -1, and then 5, 0 is 1, 2, 3, 4, 5. That's going to be a point here. Then I'm going to have 4.5, 1. You got 4.5, 1 is going to be right here, and you have 4 1/4, 2. And now it's going to be about right here. Guys, I'm really interested for you to tell me which method that you prefer, whether you prefer just going straight at it with the XY chart, or if you prefer the transformation map when we compare the parent function to the new function using those transformations. Which method spoke to you clearer? Now we're going to connect our points, knowing that we're close to the vertical asymptote, going through each point here, and arrows on both ends. And this is the graph of the function, guys. Done and done. Now let's make sure that we have our domain and range. You'll have a domain of 4 to positive infinity. You'll have a range, which is all real numbers, negative infinity to positive infinity. And now you'll want to red box it, guys. That's right. Put a box around your answers. Show off for your teacher. That was problem number 5. Let's move on. Here we have our final problem, problem number 6, and we have h of x equals to log of 1/3 of x plus 1 minus 5. Your vertical asymptote, you're going to set the argument of x plus 1 equal to 0 in order to find out what that is. Subtract 1 to both sides to find that x equals to -1 is the vertical asymptote. Red box it. Then, knowing that at -1, the function is undefined, we're going to look for what happens when x plus 1 equals to the reciprocal of 1/3, which is 3. We'll need to subtract 1 to both sides, right? And you'll end up with x equals to 2. So when you have x equals to 2, then that means that your argument is going to be the reciprocal, and therefore that immediate result is -1. Then -1 minus 5 gives you -6 as a final result. All right, so don't forget, once you simplify the logarithmic part of that equation, that you'll also need to subtract 5. All right, and now here you guys, let me once again show you what that is in slow motion. You'll have f of 2 equals to log of 1/3 of 2 plus 1 minus 5. This gives you log of 1/3 of 3 minus 5. From there, you'll have log of 1/3, and this is 1/3 to the negative first power minus 5. The log of 1/3 and 1/3 will all simplify to leave you with -1 minus 5, which equals to -6. So this was the process used in order to generate that y value. Moving on, what value will we need to generate a 1 for the argument? Well, in that case, you'll say x plus 1 equals 1. You'll subtract 1 to both sides and find out that x needs to be 0. Well, if the argument here ends up being 1 when you plug in 0, well, that means that you'll end up with 0 minus 5 to simplify, which gives you a result of -5. All right, once again, just plug in this value of x, guys, after you figure out what that argument is, and you'll be able to generate that by simplifying the result there. Then you want to find out what happens when x plus 1 equals to your base to the first power. So what do we need here in order to end up with 1/3 as a result? Solving for that, you'll subtract 1, and you'll have x equals to -3 over 3 plus 1/3 to give you -2/3 as a result. So we need to plug in -2/3 to ensure that we end up with 1/3 to the first power as the argument here. Well, in doing that, you'll have 1 minus 5, which ends up giving you a result of -4. So this process helps you generate the x values that are going to work out well when it comes time for you to graph it. Finally, you want to find out what happens when your base is squared. 1/3 squared is 1/9. So you'll have x plus 1 equals to 1/9. When you subtract 1 to both sides, you'll end up with x equals to -9/9 plus 1/9 to give you -8/9. This value, it's -8/9 that you'll want to plug into the function to guarantee that the argument is your base squared, aka 1/9. Because it's squared, when you simplify that logarithmic part of the equation is going to generate a value of 2. 2 minus 5 will give you -3 for your y value. And it's going to be these points that you'll be able to graph your logarithmic function right here. Let's check it out. So here we're showing our original function here. You have your vertical asymptote identified as x equals to -1. So let's go ahead and graph that first. So x equals to -1 is a vertical line, a dashed line that we're using for the vertical asymptote at x equals to -1. Arrows on both ends, guys. And then your other 4 coordinates will give you the points that you need to graph your function. We'll be plotting 2, -6. So 1, 2, and then -6 is 1, 2, 3, 4, 5, 6 is here. And then you have a point at 0, -5. 0, -5 is here. 1, 2, 3, 4, 5. Okay. Then you have a point at -2/3, -4. -2/3, 1, 2, 3, 4 is going to be here. And then you have a point at -8/9, -3. That's almost to -1. So -8/9 and then -3. 1, 2, 3. So that's going to be about right there. Okay. So with that in mind, guys, let's go ahead and graph this. We're going to keep it close to the vertical asymptote. And then make sure we're going through our points. Arrows on both ends. And this is the graph of your function, guys. This is it. So now let's come up with our domain and range. We know that our domain is going to be from -1 to positive infinity. You also have a range of all real numbers. That's -infinity to positive infinity. All right. And once again, let's red box it. We have x equals to -1. We have our domain, which is -1 to positive infinity. We have our range, which is -infinity to positive infinity. And that is going to do it, guys, for this video on logarithmic functions. Be so kind as to go ahead and once again subscribe to the YouTube channel, Fort Bend Tutoring. If you're able to, please donate, as that helps us bring you more math tutorials from me, Mr. Whitt, and Fort Bend Tutoring. And also go ahead and click on that like button if you made it to the end, guys. I really appreciate you spending time with me, Mr. Whitt, and Fort Bend Tutoring today. Peace. Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.